Today I want to talk to you about continue on the topic of a brief introduction of motor learning. So I'm speaking to all of you today, and all of you are experts in motor learning. How are you experts in motor learning? So you managed to made it here today. You got here from the train or the bus or the traffic jams in your car or walking, and you managed to negotiate your way through the slippery surfaces in the university after the rain, maybe adapting your situation, dealing with all the obstacles on the way and other people, and you all made it here, so that's great. So you're all experts on it. So today we're going to talk about some of these things, and of course, many of these facets of motor learning, maybe you didn't even notice today that you changed your gait patterns today because the surface was wet rather than dry. So you would have changed your gait patterns so as in order not to slip, and we'll talk a bit about how that fits into things. And I apologize in advance that I'm going to miss out lots of things because it's a brief introduction to motor learning. So of course, if you'd like to learn more, there are lots of courses at the university and other things you can take to give you a more in-depth understanding of motor learning. And on the last slide, I'll put up a few of my favorite sources. So what is motor learning? Okay, so what is motor learning? This is also I took from one of the Krakow review papers. So motor learning is any experience-dependent improvement in performance. So we have a few parts here. So there has to be some improvement in performance. So you have to be able to do some motor task better. And there's also the experience dependent. So it has to be related to something that you did. So for example, if you broke your arm and it's in a cast, and so you can't move your wrist, and then after eventually they take off the plaster and you can move your wrist anymore, that's not really dependent on your experience. That's probably not motor learning. Whereas if you spend every day doing some activities with your wrist and then you get better, so we would call that motor learning. And motor learning involves both skill acquisition and skill maintenance. So skill acquisition is when you're learning to do some new skill for a new time, you've decided to take up a new sport and you need to learn how to perform the actions, or you decided you want to learn how to do ballet or start drawing calligraphy, so you need to learn new motor skills. But importantly, motor learning also involves skill maintenance. So we have skill maintenance also on the short term and also on the long term. So on the short term, sorry. Yeah, if there's any, and of course, feel free, if you have questions and you prefer to ask in Hebrew, that's perfectly fine. And if I start talking too fast in English, which is my habit, just do like this and I'll slow down. So skill maintenance is where we need to change the way we do motor tasks because the other things change in the environment. So you can imagine on the short term, your muscles might get fatigued. You might have a sore arm, so you have to change the way that you do tasks to do them differently. Or today, for example, the surfaces outside are wet and slippery, so you need to change your gait patterns. While your goal is still the same, to get to the conference on time, but you need to change the way you do it. And then we also have long-term skill maintenance. So things change. As a child, as you're growing up, obviously your proportions and your different parts of your body are changing. As throughout the year, as your weight changes, your height changes. If you're getting older, you're less skillful at performing things. You have more variability in your movements due to disease, due to growth. All these things require also just to maintain the way we perform the same skills. And when we're talking about learning, we often want to, when we do experiments in the lab, we usually want to quantify learning. We have some paradigm and we want to test whether people get better. So we usually use learning curves or performance curves. But it's important to remember the difference between learning and performance when we do things, because how do we know if someone actually got better? How do we know if somebody learned a motor skill? So it's not really trivial in general to measure learning. What we usually measure is actually performance. So this is for an experiment we did a few years ago, which was just measuring one of these finger opposition tasks, and we count how many times can you do this in 30 seconds. We can see that people get better at the task over at the beginning they get better, they do some training here, and then they get better again afterwards, and this is when they come back after after 24 hours. So we can see they got better in this specific performance measure. But if you want to know did they learn, then it's sometimes a more difficult question to answer. You can imagine doing some task where you need to, for example, draw a maze, draw within a maze, and we could then count how fast you do the task and how accurately you do the task. So this was actually a project from master's project from one of my students. She did this task, and all the kids got much faster at doing the task, but at the same time, they also were less accurate at doing the task as time went on. So the question here is this motor learning? They got better in performance. They got better in one thing, performance, the speed, but they got worse in another thing, in performance. So there are ways of quantifying learning, but we have to remember in general that when we look at learning curves, we may be looking at performance and not learning. And you can see an interesting thing here that learning starts off quite fast, and it seems to be reaching a plateau as we get to here. I'm going to have a talk straight after this of Gil. So he's going to talk to us a little bit about learning and plateaus after this. So speaking about what's coming up today, we're also, Alfred Donkin's going to give us a talk later on this afternoon about implicit and explicit motor learning. So I'll just mention the topic very briefly, and I'm sure he'll explain to us about it in more detail. But in general, motor learning involves both implicit and explicit components. So explicit motor learning is motor learning that requires attention and demands a higher cognitive load. So you can imagine it's things more strategy-based, where you're thinking about how to perform a task. If I ask you to do some particular task, you might think about what are ways that I can do this in order to move faster. And implicit motor learning is learning that takes place without awareness. So in general, when people talk about motor learning, they usually say that explicit processes likely are more important at the beginning, and then implicit processes play a role at the beginning and become more important as we go along. And so this has usually been considered turned into these phases of motor learning. The most popular ones are Fitz and Posner from '67, although people were already talking about phases long before this, and there are many different, if you look in different textbooks and different papers, there are different measures of phases, but in general, the Fitz and Posner is probably the most popular one. So it starts off with this is just from a recent review paper. They use different names, but it's the same idea, and this is just a random axis of how it would be performance, how someone's getting better at doing a task. And you can see that at the beginning, the task is more explicit, and at the end, it's more implicit, the way you perform it. So when you start learning a new task, you're starting learning to throw a ball or learning to drive a car. At the beginning, you improve a lot and relatively quickly. And this is the stage that's considered the cognitive phase, where you need to spend more attention on it and concentrate on it. Then we get to the associative phase, where the improvement is less, but also the cognitive demands are less. And then finally, we get to the autonomous phase, where the explicit demands are very low and our performance steadies off. We also, in terms of variability, this also variability tracks also with this. At the beginning, when we start to learn a task, we're very variable in the way that we do it. And when the task becomes more automatic, we can see that our variability goes down. And we also talked about cognitive load. So the cognitive load at the beginning is very high, and the cognitive load goes down with time. So an example of that, if I'm guessing most of you learned how to drive a car, where when you start to drive a car, it's really hard. You need to concentrate a lot on the wheel, on dealing with the wheel and the brakes and the pedals and everything else at the same time. And it's hard to imagine doing anything else at the same time as you're driving a car when you start, and mirrors and looking behind you and back and your speed. It's really a huge number of things to concentrate at one time. It's definitely very cognitively demanding. And after you've been driving for a few years, you can drive more or less without concentrating at all. You may have that experience where you just drove for half an hour and you don't really remember driving, and it happened basically automatically the whole way. So it's a nice example that we see from day-to-day life, where it moves from being extremely cognitive demanding to being having very low cognitive demands as we get to the later stages. Other models do exist. For example, there's the Bernstein model of 3 levels of phases of motor learning that are related to the number of degrees of freedom that we use, when we use more or less degrees of freedom as we're learning. Okay. So one other important issue with when we talk about in learning is the topic of feedback and variability. So if we're performing a task and we want to know, am I doing the task better? We need some sort of feedback to help us understand that. A lot of tasks have inherent feedback. So when you're driving, you have some inherent feedback if you're staying on the road or if you're doing some other tasks. But we also often use augmented feedback. So we have some feedback that comes from perhaps from an external source. And in general, in motor learning, that this feedback is divided into augmented feedback is divided into two classes. So it's knowledge of results and knowledge of performance. So knowledge of results is something that's verbalizable. So you can say how someone did it, how did you perform in this particular task. It's also terminal, so it's at the end of the task and about the outcome. So you can imagine it's something like if you're throwing a ball in a goal, it can be, if you're thinking about handball, if you're throwing a ball in a goal, whether you got it in the goal or not, or how close you were to the center. I think that would be an example of knowledge of results. And knowledge of performance is more feedback about the way you did the pattern. So for example, if you bent your arm, your elbow too much while you're throwing the ball, that would be an example of knowledge of performance. So the coach might say to you, you need to perform the movement differently or use your shoulder more when performing. Related to feedback is also the issue of variability, something I'm very interested in. So we know that variability also plays an important role in motor learning. We know that variability changes as a function of time. We know that in different populations we have some motor disorders involve much higher levels of variability. We also know that playing with variability can perhaps enhance motor learning. Well, it's somewhat controversial. Okay, so once we've learned something, of course, we'd like to remember it. If we learn something in the lab, we do these short-term studies in the lab. We test them all in one day. We saw they learned something, which is great. Sometimes we bring them back a day later or a week later or a month later to test them. So this is retention. And obviously in real life, this is maybe more important than in our lab studies, because if you teach someone a motor skill, it's important that they learn how to use it. So we call this retention, the ability to maintain the skill without requiring further practice. But also important is the concept of transfer. So transfer is when the ability to apply the motor learning to a new task or concept. So for example, if I learn to throw a ball from one place, if I'm able to then throw the ball from further away or from a different place would be an example of transfer, or if I can do related tasks. So we want to, and the way that we do the motor learning, of course, will affect our ability to transfer it to other tasks.
So just say that sometimes in coding, they cannot hear the question from the audience.
Okay, yeah. So the question was, an example of retention from real life. So basically, any task you do when you come back. So if I'm in a task in the lab that I perform might be playing something on the piano, and then I bring you back a week later, a month later, and they say, in the lab. Okay. It's a general sort of term. So for example, if you were in a rehab setting and you were, like the example that Shai was showing about putting on a piece of clothing or performing a test with pegs, or you can think about in real life. Well, it could be walking. Let's say, for example, you're at the clinic and you have some issue with your walking. You have asymmetrical gait, and you'd like to improve your gait quality, make it more symmetrical. It's a suitable treatment for you, and so you come to the lab and you perform the walking. And then the question is, if you come back using some technique, so for example, maybe using a split belt treadmill or some other technique, they get you to walk more symmetrically. Now, if you come back a week or a month later, have you retained the skill?
The classic example in day-to-day life is falling off the bike. I mean,
riding a bike. Okay. Okay. Yeah. So Offer's example was if you learn how to ride a bike, and then 20 years later you come back and you still remember how to ride a bike. So that would be a nice example. It's obviously it's very important if we teach someone to do a motor task for the purpose of rehab. If there's no retention, then it's kind of probably wasting our time. I mean, so maybe we have to think about how we can enhance retention. I mean, maybe it requires further practice or further attention on it. definitely an important issue. We don't want people just to
So
learn.
the motor learning was in this day or in this period for short,
Mhm.
and then when you test and
We test them again later, yeah. So we test them again after a week, a month, depending what the task is, what the relevance would be. Then we'll test it again. Okay. Where does motor learning occur? I always get a little bit scared of these pictures of the brain, and so I think Roy's going to talk a little bit about this in his talk later today. So you can see basically the main reason for showing you is that it's like most of the brain. There's this some reason. This is also from this review paper. The visual areas, which definitely are involved in learning as well, are not lit up here, but lots of areas of the brain are involved. And Shai talked a little bit before about neuroplasticity is one of the important topics in motor learning. How do we, and a lot of people are interested in questions of how to increase neuroplasticity, whether it's using drugs or using electrical stimulation or magnetic stimulation, TMS or TDCS, or other sorts of techniques that can increase brain plasticity to improve the learning process. So we have different mechanisms we can think about for motor learning. This is from another review paper from a couple of years ago. And this one, they talk about 4 different types of mechanisms that range from high cognitive load to low cognitive load. So the first one here is instructive methods. So instructive methods is using an intentional motor strategy. So you can imagine these are things that are also highly cognitively demanding. So you can imagine something like if it's walking, you might be saying to someone, okay, take a bigger step with your left leg. I can see your left leg is not moving enough, so I want you to take a bigger step with your left leg. So you can imagine that these things are strategy-based and explicit. It's very clear. I'm telling you this is what you should do. It requires knowledge, external feedback, knowledge of performance, so you can see if you're doing it or not. And here they talk about the neural substrate being the prefrontal cortex, so something that requires a lot of cognitive load in order to perform. Second level they have here, which is slightly lower cognitive load, is reinforcement or reward-based learning. So this is driven by some sort of binary outcome base. So you have either yet succeeded or didn't succeed in the task. This is obviously related to reinforcement learning, which if you dabble a bit in machine learning, this is a very popular topic at the moment. And so this you can imagine as a task, for example, if maybe you're throwing a basketball into a net and the feedback you get is I succeeded or I didn't succeed. And eventually, so based on this feedback, you will eventually change the way that you throw the ball to get better. So here we get here knowledge of results instead of knowledge of performance. So knowledge of results, you remember, was success or failure. And this is thought to involve mostly be related to the basal ganglia, related to reinforcement learning. The third one is use dependent. So this is where we repeat some very specific tasks. So you can imagine, and mass practice, you can imagine it might be learning how to putt in golf or playing tennis. So if you're practicing putting and you're not very good at putting, the hole is there and your putter is here, and you'll just do it over and over and over again. And eventually, after you do it lots of times, you'll get better. So we have this, we talked a little bit about this massed practice. So you do lots of practice here. This is believed to involve mostly the motor cortex and the spinal cord. And then we can also think about this in rehabilitation settings where you have someone perform a task and they repeat this task over and over again. And the last one is sensory motor adaptation. This is what we talked about before. For example, today walking when the surface is wet, and you have to adapt the way you perform the task. So this is not generating a new motor program, but rather changing the motor program. You can imagine this in other things. In the lab, we have specific paradigms that look at this by altering the feedback people see or by having people move in force fields. But this is also something that we definitely deal with in day-to-day life where we have some adaptation. So it can either be things like this slippery surface, or it can also be like I talked a little bit before about having a split belt treadmill, which then induces some error in the way that you walk. So you have to, if one belt of the treadmill is moving at a different speed, you need to correct do it, and then we might, hopefully there'll be some after effects that might improve your walking after that. We can see that the cognitive load is different in this. So this, from this side where we have to think a lot, these ones we have to think not so much. I think I'm talking for a little bit too long, so I'll conclude in just a minute. And just to finish off today, these are lots of questions, and I'm going to give you 0 answers, but it's things that we should think about. And for each of these things, there are lots and lots of research papers already on them, but a lot of them are still open questions. So these are things we think about in the field of motor learning. Massed versus distributed practice. Is it better to practice 60 minutes one day, or 6 times 10 minutes, or 60 times for 1 minute? Whole versus part learning. If I'm learning juggling, should I learn to juggle all 3 balls at one time, or should I start with 1 and then go to 2 and then go to 3? So we actually had a paper about this last year. You can, I can explain to that more about you later if you're interested. What's the role of variability in motor learning? So do we want to have more variability, less variability, at what stages, and what sort of variability are we talking about? Which type of feedback is optimal? How the effects of using different types of feedback on motor learning? How hard should we make our tasks in motor learning? So if you have a task and it's too easy, probably you'll not learn anything. But if the task is too hard, you'll also not learn anything. There's a lot of in music literature, for example, they talk a lot about this idea of desirable difficulty. If you get stuck on a piece, if you reach a plateau, then you can make the task even harder. This desirable difficulty to help you learn it. What's the role of motivation when people are learning? Particularly in some populations, they're using reward or punishment to helping people perform motor learning. Attentional focus. How important is it that I devote most of my attention to learning a task? Are there things that I can learn better without attending to them too much? We know that the sleep and consolidation have an important. Consolidation is the learning that occurs during sleep or when we're not actively performing the task. So what's the role of sleep? And one of the speakers, unfortunately, wasn't able to make in the end, Maria Coleman. She's done a lot of studies looking at the time of day for learning. Is it better to learn in the morning or the evening? And how does this relate to special populations? For example, people with ADHD or older adults, what time of day is best for them to perform learning? Which is related to the differences in learning at different ages. If I want to teach something to a young adult or an old adult or a child, how would I teach them in different ways? What about dual tasking? If I learn 2 things at the same time, or if I increase or decrease the cognitive load, how does this change learning? And then there's still a lot of open questions about are there different types of learning, and can we get to some sort of a personalized learning to optimize learning for a specific individual? So I'll finish without answering any of those questions. I'll finish here today. These are the main reviews that I took things from today. At the end, we're going to send we'll send out the PowerPoints for all the speakers who agree, and I agree. So these 2 books as well are nice. Before we had this motor control network, I used to organize it was called the Motor Learning Hub, and we actually, most of the videos are still online. So if you click on this link here, once you get the PowerPoint, then it has a nice, there's a collection of, there's a collection here of all the videos. We had a bunch of nice speakers give talks on different motor learning related topics. And last year we also, I think it was last year, we organized a meeting on slow movements, why it's difficult to produce slow movements, what the connection is, and a bunch of you are also there for that meeting. But if you missed the meeting, then the videos are also online, so I encourage you to take a look. Thank you.